All right, everybody, thank you so much for joining us today. We're going to go ahead and get started with our live webinar. I am going to go ahead and just introduce myself. My name is Janet Page. I'm the Senior Marketing Manager at MacTac. I'm responsible for medical and industrial tape products. And joining me today and really carrying the weight of the webinar would be Steve Schroff. So Steve, I'll let you go ahead and introduce yourself to our attendees.
Okay, I'm Steve. I'll be covering most of this presentation. I'm a business development chemist here at MacTac, and I've been here for about 18 years now.
Great, thanks, Steve. So just a little bit of background about MacTac. We are located in Stowe, Ohio. Recently acquired the Duramark operations, both in Spartanburg, South Carolina, and Minneapolis, Minnesota. We've got 6 distribution centers across the U.S., and our 2020 sales were totaling just about $5 million. So MacTac is owned by the Lintec company, which is a Japanese pressure-sensitive adhesive manufacturer. And we were acquired by Lintec in 2016, and it has been a fantastic partnership for MacTac. And has really allowed us to flourish and expand into new technologies and new markets. Within MacTac, we have several different business units. The first of which is our graphics division. Our graphics division focuses primarily on wide format and screen print media, amongst other things. Steve and I both represent the industrial and medical tape division, where we focus on specialty products for industrial and medical applications. Next, we have our sheets division handling all things offset and digital. Within the same group, we do a narrow roll division, and they do narrow format aqueous and inkjet type printed materials. And then finally, we have our roll label business, which handles prime films, durable films, label materials for on-demand printing, amongst other things. And the roll label business might be the one that MacTac is most known for in North America, but certainly we're making a name for ourselves in the industrial and specialty tape world pretty quickly. So we'll go ahead and move on to the next slide.
Yep, so this is where I'm going to take over. And I just want to say to everybody on the phone or listening on the internet, we are having some really bad storms here. So if it does look like this freezes or cuts off, please be patient. If we do lose power, our generators will kick in, but it does take a little bit for the system to kind of get up. So if it does seem like it stops, please give us a few minutes, for us to log back on. Our facility is backed up by generators, but not sure what the weather's going to do, but we've been getting some nice, much needed rainstorms here. So this talk is titled the differences between UV solvent and acrylic, solvent and emulsion acrylic adhesives. So here we have the first slide is that I'm taking over here is adhesive types. So just reading through here, these are all the adhesive types you've probably heard being used out there by pressure sensitive adhesives coaters throughout the industry. Very common: solvent acrylic, solvent rubber, emulsion acrylic, UV warm melt or just UV acrylics, hot melt rubbers, emulsion rubbers, hot melt acrylics. All these are different types of pressure sensitive adhesives that do exist out there that can be utilized. So really what we're talking about here is that every time you hear rubber or acrylic, or even if we're talking silicones, although I don't really cover silicones in these because they're a very small part of the industry, but what we're really talking to is the base chemistry of the polymer, the adhesive itself, really the framework that everything is built upon. If you hear rubber, you hear acrylic, it's a rubber or acrylic based adhesives, and then everything else, solvent, emulsion, hot melt or warm melt, that really refers to the delivery method of the adhesive, how we're getting the adhesive onto the web. And that's an important point in that, pressure sensitive adhesives really only are useful if they are coated in a tape form or on a web. You can certainly dispense pressure sensitive adhesives the same way you would dispense, say, structural adhesives, but it really kind of takes the utilitarian or the utility out of them of being a tape and just being applied. So we really need to get them onto a web. So when we talk about how we do it, well, solution is that we're using some type of liquid carrier. Solvent-based adhesives are using organic solvents to dissolve the adhesive polymer. This could be your toluene, heptane, hexanes, MEKs, ethyl acetates, alcohols, things like that. With emulsions, we're using water. All the adhesive polymers are dispersed in water. These adhesives can range in viscosities from 500 centipoise to 25,000 centipoise. To give you an idea, water is 1 centipoise at room temperature. And so really the purpose here is that if you try to measure the viscosity of an adhesive that's already been casted out and cured, it'd be in millions, maybe tens of millions centipoise. So we got to find a way to get it onto the web. Solution is one part, or is one solution adhesives is one solution where we're actually dissolving the polymer into a solution, make it coatable. Another way we could do this is actually turn it into molten form, which is your hot melt adhesives. Hot melt, we're coating them, or we're melting them at about 300 to 400 degrees Fahrenheit. We're making the adhesive molten, so it's down to a coatable viscosity. Warm melts are the same type of it's the same concept. It's just we're just using a lower temperature, hence warm melt. So they're typically done anywhere from as low as 150 Fahrenheit up to 280 degrees Fahrenheit. That's really the difference between warm melt and hot melt. Other than that, they're exactly the same. You're applying heat, you're making it molten, and that's how you're coating it. The viscosities of hot melt and warm melt adhesives are quite higher than that of solution adhesives. On the low end, you get maybe 5,000 centipoise. On the high end, you're going to top out about 150,000 centipoise. So again, 150,000 times thicker than what water would be. So, and again, with this whole presentation, I'm going to start really high level and kind of bring it down into the weeds. I really want to start high level because it gives you an idea of why these adhesives perform the way they do and the differences. So starting again, high level here, you've heard me say this before, define as pressure sensitive adhesives. Well, they're viscoelastic materials, which is a fancy way of saying they're both liquid and solid at the same time. The visco part of the adhesive is what allows for the wetting out of a surface to form the bond. The elastic is what we call the solid part of the adhesive, and that's what resists deformation. That basically means you can't deform the bond. So an example I usually give here at this point would be maple syrup. Maple syrup is very sticky. You get on your fingers, it's very tacky, it's sticky. The problem is that, you know, it doesn't have any resistance to deformation. It doesn't have a lot of molecular weight to it or guts, and so you can very easily separate things apart from it, even though it's very sticky. Pressure sensitive adhesives, they have just the correct balance between the liquid and solid components. We usually refer to this as the dull course criterion. I'm not going to go into it, but Janet hates when I use that term, so I like to throw that out there because it makes me smile. But really the point of the pressure sensitive adhesive is to balance the liquid component, which makes the bond, versus the solid component, which actually helps maintain and keep the bond. This is largely driven by molecular weight, or what we call molecular weight, which is really the size or the length of the polymer chain. In previous webinars, we had some fun, and I defined this by using pasta. On the left here, you got some macaroni and cheese with some elbow macaronis, and this is really representing a smaller polymer size. A smaller noodle, it's very easy to reach in there with a fork or your fingers and pick out a single noodle at a time. There's not much resistance, versus something that would have a higher molecular weight, or your spaghettis on the right hand side, which is a larger noodle. It's very much harder. It's very hard, much harder than to reach in and grab a spaghetti and pull that out from the bulk. You're going to end up pulling out a lot of spaghettis, and you know there's a lot of entanglement there. We call that molecular entanglement. And again, everything that we're covering here is really driven by the fact that we need to coat the pressure sensitive adhesive onto a web. That's where it's getting its most value. The problem is, and why I'm talking about molecular weight is that in order for the adhesive to be of the proper molecular weight, and so that you can make a bond and hold a bond, it makes it very uncoatable. It's not really very easily coated. In some cases, it's impossible to coat. So how do we get around that? So how we get around that is adhesive curing, or what we call cross-linking. What we do here is, and this is mostly for acrylics. So, and with the acrylics, I'll be covering in this section really the solvent-based and UV cured acrylics. They are the ones that cure. And this is the fundamental difference between acrylics and rubbers. Again, acrylic adhesives have the ability to cross-link, which gives them all their properties. that are so much different from rubbers. So it sets it apart from rubber-based adhesives. It also sets it apart, as I'll cover a little bit here, from emulsion adhesives as well. So how we get an acrylic adhesive onto the web is we coat it on at a very low molecular weight, much lower, far too low that would ever make a good adhesive, but it does allow us to get it onto the web. And then we cure that adhesive, or what we do is we call, or cure, sometimes called cross-linking. And this happens in 3 different ways. One, you can have the solid evaporate. So in the adhesive, and this is your self-cross-linking types of acrylics, most of what's coated today for acrylic, solvent acrylic adhesives are self-cross-linking. You have a catalyst in there, we call it a metal chelating agent, but that's what kicks off the reaction, and it's surrounded by an inhibitor, which keeps it sterically hindered, which means basically there's these big molecules that doesn't allow that little molecule out to go find reactive sites. And as the solid evaporates, that inhibitor evaporates, and that's how you get the self-cross-linking. So that's already built into it. There's no need to add any secondary cross-linker. Another way of doing this is initiation temperature. Sometimes they're out there. They're not very prevalent, but they still do exist. Now you have reactive groups in the back of your polymer. You get the web up to a certain temperature, that kicks off a reaction. That reaction cross-links the adhesive. Or the other way is UV light, where you put it down as a molten syrup type viscosity, and you hit UV light. And what all 3 of those are doing essentially is you're building the molecular weight to the point where you're back into the pressure sensitive range. You're hitting that Dahlquist criterion. So you're going from something that's very liquidy, again, capable of wetting out surfaces and forming a bond, but not solid and can't resist any deformation, to something that has the proper balance. And on the right hand side, I just have 2 examples here. I have something of a lower cross-link density. So each one of those, this is a rough exaggeration of what it looks like. The blue being the polymer backbone of the acrylic, and the red just being the cross-links. You can have low cross-link densities. You can have high cross-link densities. With solvent-based adhesives, you can even throw in an extra cross-linker and firm it up. There's no set cross-link density per se. This is one of the ways with acrylics you can tune the properties, is how much cross-linking you have in there. So now, a question I get a lot is difference between solvent and UV acrylics. And one of my favorite examples that I'm starting to use for explaining this is looking at a Tesla, or basically an electric car, versus the old tried and true internal combustion engine. So I think this is a Toyota Camry I borrowed off the internet or something. So we have a Tesla and a Camry. Both are passenger cars. Both have 4 doors and a trunk. Both are capable, as far as I know, of holding 5 passengers. Both have 4 wheels. Both rely on the same type of tires. Both drive the same controls. The difference is that we're switching out the tried and true internal combustion engine that's been around for 100 years, and we're putting in actually the tried and true electric motor, which most people don't realize the electric motor itself has been around for 100 years itself. The difference is that the electric motor usually isn't used in cars. It's tried and true. It's proven technology. It's been around for a while. We're just now starting to put it in cars and replace the, again, perfectly serviceable, nothing wrong with the internal combustion engine. That's how I view a lot of the differences between solvent and UV acrylics, and you'll start to see why. So when I say what's the difference between solvent and UV acrylic, very little. There is very little change or differences. The only thing is a change in the initiation or the cross-linking. In this, most adhesives, that accounts for maybe 0.1% of the formula. The monomers that go into making the backbone of the acrylic adhesive are the same in a lot of cases. Well, they're actually the same, and in a lot of cases, some of the vendors out there we worked with just to simply take a old solvent adhesive we had, remove the thermally initiated cross-linker, and put in a UV cross-linker. Everything's basically the same, except we just changed how those 2 adhesives cross-link. Again, they're still cross-linking, it's just a change in how it happens. And what we see is, they both have similar peels. There are solvent adhesives out there that have high peel. There are UV adhesives out there that have high peel. In general, acrylics themselves, in general, solvent or UV, max out at about 10 pounds of peel. There are UV and solvent acrylics out there that have high shear. For us, 300 hours, we say 300 plus hours at a kilogram. Basically, at 300 hours, we give up. We take the shear down because we just assume it's not going to fail. So that's essentially maxing out the test. And we can max out those shear tests with UV, and we can max it out with solvent-based adhesives. They're both going to have similar high temperature range, which is about 454 acrylics. Getting much higher than that, you have to go into the silicone-based adhesives, but there are UV options and there are solvent options that are going to get you up to that high-end temperature range of about 450. Both have similar LSE. Now, acrylics as a whole do not have good LSEs. I won't say that they make great LSE adhesives. They're nowhere near as good as rubber, but acrylics can be modified with tackifiers to have LSE properties. This can be done with both solvent adhesives and it can be done with UV acrylics as well. And they have the similar chemical resistance. Again, the fundamental difference between acrylics and rubbers or solvent UV acrylics versus emulsion acrylics is that they're cross-linked. And that cross-linking is where you're getting your temperature resistance, and that cross-linking is where you're getting your chemical resistance as well. Again, both of these adhesives are cross-linked, so you're going to have similar performance for chemical resistance and temperature resistance. Both have similar UV resistance. That's more of the backbone of the polymer of acrylic versus cross-linking. But again, both could be used in direct sunlight and withstand that for years. So if they're so similar, why UV acrylics? Why did the UV acrylics come about? The first thing I mention here is that UV acrylics really came about mainly because of the processing and handling, not because of any shortfall in performance properties, anything that you would see at the end use application. So we're seeing UV acrylics because they're more efficient in the coating process. No solvent equals no drying equals higher line speeds. The drying of the solvent or even the water, and if you're talking emulsions, but the drying of the solution carrier will always be the rate limiting step when you're talking about solution-based adhesives. If you eliminate the drying, you certainly can move a heck of a lot faster in terms of your line speeds. You're also lowering your energy costs. Again, those ovens, they are burning a whole lot of natural gas in order to generate the heat needed to drive off the solvent carrier or solution carrier, solvent or emulsion. These ovens could be 60 roll label, they could be 80 some inches wide and 300 feet long in some cases. It's a lot of natural gas. And then you also have the thermal oxidation for the solvent-based adhesives, where you actually, EPA says you can't just blow solvents, VOCs in the atmosphere. You got to recover them or you got to burn them off. There are regulatory benefits. You don't have the permitting or the disposal, any of the emission hassles, or any of the EH&S hassles with the UV that you do with the solvent. Again, environmental health and safety. Through my years in the industry, 20 now, we've seen plenty of fires, some explosions at churns. One of my former employers, their coating facility, one of their facilities burnt to the ground. So you don't have that with UV acrylics that you do with working with solvents. And then the environmental benefits, again, no VOCs and a lot lower carbon footprint. And this really goes back to burning the natural gas for the dryers. Our new coater that we built to run the UV acrylics and a lot of the hot melt rubbers, in an entire year, that thing does not consume 1 month's worth of natural gas on one of our old solvent lines fired. So much lower carbon footprint. And that's really why the acrylics came, the UV acrylics came about. Again, it wasn't necessarily that the solvent acrylics weren't meeting any certain performance requirement. When you look at your traditional properties of adhesion, it's more around the handling of it and the manufacturing of it, the efficiency of it. It's just the next step in the evolution, a lot like the electric car is with versus the internal combustion car. However, there are some advantages of the UV acrylic that aren't necessarily very obvious on the surface. One of them is that with the UV acrylics, you can get much higher coat weights. Solvent-based adhesives, you pretty much top out about 5 mils. There are some UV acrylics out there that are coming there. They're free radical cured. And the vendors out there are touting up to 15 to 20 mils in thickness. Right now, we don't coat any of them. We have evaluated them. We're just waiting for the right opportunity. But with the UV acrylics, you can get much higher with the right kind of curing system. You can get much higher coat weights or coating thicknesses than you ever could with any solution-based adhesive. non-VOC, non-outgassing, and non-migratory. I'm going to put all these together. So when you see these three, you really think of environmental impacts. But what we found is that, you know, with VOC and outgassing, when I get to emulsions, I'll cover outgassing is a little different than VOC, and migratory, anything that might migrate. There are certainly markets out there that do certainly benefit from these properties. Electronics, your high-end electronics, and your medical diagnostics are the two that come to mind. As electronics get smaller, there's no thermal mitigation there. Basically, what I'm saying is there's no fans. iPhones, iPads, a lot of these devices don't have fans. These electrical devices get really hot. So as they heat up, if there's anything in that adhesive that's going to outgas, eventually when it cools down, it has nowhere to go because there's nothing venting any environment. In fact, a lot of times these devices are sealed so that you can drop them in water and they're not destroyed. So whatever's getting outgassed is going to stay in there. It's going to condense, and it's going to condense on that very delicate printed circuitry that's in there. And if you have a lot of unreacted monomers that typically exist in solution-based adhesives, that does eventually eat away at that circuitry, and then you start getting antenna failures or certain different failures in there. You start degrading circuits. In terms of medical diagnostics, most of my career has been in medical adhesives. It's amazing what you can get away with sticking to skin. That's what skin is there for, is to protect the delicate chemistries inside the body from all the environmental factors outside. But with diagnostics, now we're talking like blood glucose, different cardiac monitors, pregnancy tests. You're taking all those chemistries from inside the body, and now you're putting on them a chip, and they're very, very delicate to any type of outside influence. So you have to have adhesives that are very, very clean, nothing that's going to migrate in there, nothing that's going to throw it out. So you do get some benefits here that aren't necessarily on the surface. Look there. Again, a lot of people pick up a data sheet and they see a peel, attack, and a shear, and they see that it's same from side to side, but it's these other little properties or attributes that kind of go unnoticed, such as the non-outgassing, non-migratory, and the non-VOC, which are advantages of the UV acrylic. Again, kind of repeating what I said before, but they're much more efficient to run. Again, when we burning natural gas, it's a non-value add. Nobody out there is going to worry about where we buy our natural gas or what type of natural gas we're running, although I think there is only one type of natural gas. But basically, you get the idea that they are non-value adds. And again, with the regulatory benefits, just not having to deal with them is such an advantage. So now we're going to talk about solvent acrylics. Are there any advantages to solvent acrylics? Well, you know, again, just like the internal combustion engine cars, solvent acrylics are still relevant, and there are still some advantages to them. The biggest one here being optical clarity. This is really one of your high-end window films and over laminates. This is where your solvent adhesives are always going to be used. So with a UV or a hot melt adhesive, you can get a good clear, and some people will refer to this as an optically clear coating, an optically clear film. A lot of what we consider optically clear really comes from going from a paper liner to a filmic liner. That gets you probably 80% of the way there. But if you're talking true water white, which is a way of saying perfectly clear, you have no idea it's there, you can use it to laminate two pieces of glass together or have it as a glass over laminate and see no distortion whatsoever. That is really a function of your solvent-based adhesive and the solvents that really slow the evaporation. When you have those types of solvents that take a while to evaporate, everything has a chance to really get nice and settle down, kind of get smoothed out, and you get a really nice coating. We have not, and a lot of work's been done out there in the industry to try and make 100% solids be as optically clear as solvent-based adhesives. It just hasn't happened. So again, you can get a good clear coating out of a UV or a hot melt rubber. You can even get a good clear coating out of an emulsion acrylic, but you're never going to get that high-end optical clarity that you will out of a solvent adhesive. Another reason why I like to compare, the electric car to the gasoline car is one of the advantages of acrylics is there's simply more of them to choose from. The technology's been around for 50+ years for self-cross-linking adhesives. There's just simply more options, just like the electric car. You have a handful of electric cars to choose from out there.
But when it comes to internal combustion, boy, you got a whole lot more. And so right now, whenever I go out and talk to people about UV acrylics, everyone always asks, well, what's the disadvantage? One of the disadvantages is that right now we don't have a lot to choose from. As the years go by, that's changing. A lot of people are investing in that, and I'll cover it. But there's still right now a lot more solvent-based adhesives to select from than there are UV acrylic adhesives. A lot of the solvent-based adhesives, because they've been around for so long, there's a lot of long-standing approvals and specifications that, again, UV acrylics can certainly meet them. It's just they have to be tested, and that's going to be a cost and time associated with that. One of the nice things about solvent acrylics is that they're much easier to modify, and because of that, they're really better for smaller custom jobs. And what I mean by modify is that tackifiers can be put into a UV acrylic adhesive, or you can put different additives into them, but it's much harder because you got to heat it up and you got to get it molten. And even then, it's still at a much higher viscosity, and you got to have much different types of mixers, specialized mixers that keep it hot. With a solvent-based adhesive, you just need a simple air mixer, or just a simple drive shaft, like a Ross mixer, and you can stick it in a drum or you can stick it in a churn, and you can just throw in a bunch of additives, and they're going to dissolve and be dispersed very easily. That simply isn't the case per se with UV adhesives. Modifications can be done. They certainly can be tailored, and modifications can be done, but it's a lot harder to do just given the nature of them and the equipment that's needed. And there's a lot more raw material options for solvent-based adhesives than the UVs. Again, a lot of the chemical companies, they're seeing the UV become more and more prevalent. They're making more and more raw material additives for UV. There's not as many to select from right now. The main problem here is they got to be heat stable and they can't interfere with the UV cure. So if you're going to put in a tackifier that absorbs UV light, well, you're not going to cure your adhesive, and everything I said about cross-linking kind of goes out the window. And that's kind of the challenge there. And the last bullet point here is infrastructure exists for the manufacturing of solvent-based adhesives. Again, for a lot of people already out there who already have the equipment, they don't need to do any investment versus, putting in new wide web UV coaters that cost several $1,000,000. Again, you already have the infrastructure out there. You're starting to see people change over. Again, MacTac, we exited solvent 2014. Granted, with the purchase of Duramark here in the past month, we actually do have solvent capability again, but when we exited solvent coating, we invested and made that big capital expenditure to invest in UV. Not everyone out there is capable of doing that, or they're not ready to do it yet because they still have, assets on their books that need depreciated. So now I'm going to look at emulsion adhesives. So I had a Tesla for UV, and I had, I think, a Toyota Camry for solvent. Emulsion gets a Vespa. It gets a moped. Its transportation is capable of getting you from point A to point B. It might get one person, maybe two there, maybe not comfortably, maybe not very fast. And if the weather changes, you might be up the creek, but it's still a mode of transportation. And this is how I'm going to pick on emulsions and say it's a moped. But really, emulsions are adhesives that utilize water as the carriers. A lot of times the monomers that you're using and the resulting polymers are very insoluble in water. So that's a trick of how they're manufactured. And how they're manufactured actually works on a lot of the same principles of detergents, dishwashing soap, and laundry detergent. And everything I'm about to show you, some of the commercials out there for like Tide show a lot of the same thing. But I'm going to show you this emulsion technology because and how they're made, because it explains so much the differences between them and their properties and attributes. So they're based off of surfactant. Surfactant is the main component of what we call soap, and they're unique polymers. And the way that soap, or surfactant in this case for adhesives, works is that a surfactant is a molecule that has a hydrophobic tail and a hydrophilic head. So basically the tail hates water, loves oil, and the head loves water, hates oil. And because of that duality, then this is how you get oil to mix in the water. And what you do is when you put them in the water, they form this. So since we're talking water-based adhesives, all the hydrophilic heads are going to be facing out, and all the hydrophobic tails are going to be facing in, and they form what's known as a micelle. Now, this is some detail here, but basically they form these big clumps, these big molecules, we call them colloids. This is the same principle as milk. And what we see here is, again, the heads are aligning out because it's an aqueous environment. The tails are lining in, and then that's where the polymer is being made. If we were talking dish soap, we'd be talking, you know, that yellow thing that's spinning in there that I have representative of the adhesive polymer. If we were talking dish soap, that would be bacon grease or fat or something like that, or laundry detergent. That would be your dirt and your grime. In this case, it's polymer, and this is how emulsions work. You need these surfactants. You get all the insolubles encapsulated in a surfactant, and then that's where the actual polymerization occurs. So again, I'm talking about this because this is how the basis of the technology. So here you got a whole bunch of your micelles in the solution, or in the solution in the adhesive. You just coat them out, and they're starting to the water's starting to evaporate, and they're starting to coalesce onto the web or the release liner. And then you add a little bit more heat, and they start to flatten out, and they're really coalescing here. And you get, theoretically, then a nice homogeneous polymer left behind. That is the theory. So looking at emulsion adhesive attributes, one of the things we notice is that most of the emulsion acrylic adhesive developments have focused on making better labels. They focus on the roll label and the graphics market. And a lot of the technology out there is focused on making them better at converting for labels, or improving the weatherability or the plasticizer resistance because they're used on vinyls. Not a lot of focus has been done on technical tapes for emulsion. And a lot of that is that, you know, I say a lot of what I talk about is driven by molecular weight. Well, emulsions are really high molecular weight. In fact, a lot of people that know adhesives and polymers are mistaken or surprised to find out that actually of the adhesives, emulsions have the highest molecular weight. But the problem is that you don't get a lot of molecular entanglement. So if you go back to that polymer web, or the web with the dried polymer, you know, I showed it as being homogeneous. In reality, though, you get more like defined kind of domains. And since, you know, when you're doing this polymerization, you're doing it in that micelle, and everything's kind of clumped together, you might get a lot of high molecular weight, but you don't get very much molecular entanglement. Those clumps don't necessarily interact really well for each other. So going back to the pasta example, okay, you're going from elbow macaroni to something much larger, much heavier, such as stuffed shells. However, the stuffed shells aren't really entangled up against each other like the spaghetti was. So it's still very easily to remove a stuffed shell versus the elbow macaroni. So that gives you an idea. Okay, it's higher molecular weight, but you're not getting a lot of interaction between the polymer chains. So there's nothing there for cohesive strength or chemical resistance or anything like that. Another reason why you don't see these used a lot in technical tapes applications is, I'm having trouble defining this, but I call it ineffective cross-linking. But essentially what I mean is that you can, despite some misnomers out there, you can actually cross-link emulsion adhesives. The problem is that when you add cross-linker, you get a lot of cross-linking that happens within the micelle. And a lot of the reasons why people cross-link emulsion as adhesives is to not make them more cohesively strong, but to actually kill the tack and turn them into removables. So this is something that MacTac does on our roll label side a lot, where we use a lot of emulsion adhesives, is that, you know, we can add some tack or cross-linker to them externally, and we could take a permanent adhesive and make them into a removable adhesive. But you can't really, you know, it does increase the cohesive strength a little bit, but you're never going to get that cohesive strength up to where the solvent-based and the UV adhesives are, mainly because you're getting a lot of cross-linking within the micelle, but the micelles themselves aren't really interacting. Now, I will say, recent developments, very recent developments, you're starting to see newer generations of emulsions improve this property. So as things are coalescing onto the web, you do get some interaction and cross-linking between those micelles. And because the cross-linking can occur between micelles and, you know, these conglomerates of polymers, you're starting to see more and more properties comparable to solvent acrylics and UV acrylics. So this is something that, you know, at MacTac, we're watching this very closely. We have some technology that we're utilizing around this, and we're going to see what we can really do and looking to push really push the boundaries of what you could do with emulsion adhesives. Again, historically, you couldn't get this type of cross-linking, so emulsions were never really used for technical applications, because this type of cross-linking is where you get your temperature resistance, your chemical resistance, a lot of things like that. We're starting to see it now. So one other attribute of adhesives, unfortunately for emulsions, though, is that we do see lower adhesion values. And again, I focused on the manufacturing for emulsions to kind of explain this. You have to use a lot of secondary additives for emulsion adhesives, and that really hurts their peel performance. The surfactants in there are going to hurt peel performance. The thickeners, you have defoamers, you have wetting and leveling agents. You even have antimicrobials in there to keep the fungus and mold down that will attack an emulsion adhesive. And a lot of why you have this is I got a graphic over here of what water looks like on a freshly waxed car. You can imagine taking a very polar molecule and putting it onto a very non-polar release liner, a siliconized release liner. It's a lot like taking that same polar molecule of water and putting it on a freshly waxed car. All your water beads up. So you have all these other additives in there really so that you can coat that release liner, because if you didn't, everything would bead up and then you wouldn't have a nice cohesive coating. And get yourself a nice, looking tape. You would get something like you see on the right, which would have almost no, no real use as a tape in the pressure sensitive industry. Those would be too thick. You wouldn't be able to dry them. The web would be too inconsistent. You never be able to slip through them. Things like that. Another attribute of emulsion adhesive is that you're going to be limited in your coating weights. 2 to 3 mil max is what you're going to see in your emulsions. Again, water is very hard to dry. Water is a very unique carrier in that it's the highest of all boiling points. So at low coat weights, you can hit it very hard, very fast, very hot, and get it dry, but that's up to about 1 mil in thickness. Above that, then it becomes a law of diminishing returns, and you start skinning it, and you can't get them dry. So with solvent-based adhesives, you can get 5 mils. With water-based, 2 mil, maybe 3 mil if you're willing to tolerate a lot of residual moisture there. So why emulsion adhesives? There had to be a reason why they came about. Well, one is that they are economical. They are the most cost-effective acrylic option that's out there. One of the downfalls to solvent is that organic solvent costs about as much as a gallon of gas per gallon of solvent. Right now, that price is climbing, gets depressing going past the Circle K every day. I think for us, gas is about $1.89, $1.85 a gallon, or I'm sorry, $2.89, $2.85 a gallon. Water is essentially free. Another thing here is economy of scale. Paint. A lot of your emulsion adhesives are based off the same raw materials that go into paint. Paint is far bigger in scale than pressure sensitive adhesives ever are. So you do get a lot of economy of scale there. And again, with your emulsion adhesives, depending on the thickness, you usually do get a lot higher run speed, especially on the roll label side. On the roll label side, those coaters can run 3,000-4,000 feet a minute. But again, you're talking very low coat weights, below 1 mil. Emulsion acrylics, especially compared to rubber, and I'm going to have a table up here where I compare all these attributes to each other with a rubber, but you still get pretty moderate temperature resistance out of an emulsion acrylic, around 250. A lot of rubbers crap out about 180, you get about 250 out of an emulsion. You do get some moderate chemical resistance, especially on the plasticizer side. You're going to get the UV resistance. Again, better than a rubber, not quite as good as a solvent acrylic, but still pretty good. And really, emulsions are good for general purpose adhesion. Again, something that doesn't necessarily need a lot of shear or high adhesion or shear strength. So again, you've seen a lot of emulsion adhesives in your labels, vinyl decal signage. You see some cheap double coated emulsion adhesives come overseas for point of sales types, things like that, displays, short-term use, just needs to stick two surfaces together. So really it comes down to what you need it for. There's nothing wrong with emulsions. They're not necessarily as high as performing. That's starting to change. It's just a matter of what you need it for. So I threw a lot of information at you pretty fast, so I'm going to just slow it down here. And I filled out this table with a bunch of different attributes. And, the 3 acrylics, and then everybody always asks, again, it always comes back to, well, how does rubber and acrylic stack up? So I have rubber on here as well. So the first thing's going to be adhesion. And your solvent UV acrylics are going to be pretty high adhesion. And this scale goes from 4 pluses to 1 negative. So again, 10 pounds for solvent acrylic and UV acrylic, pretty high. Emulsion, emulsions usually top out 5 or 6 pounds for a comparable coat weight. And then actually rubbers, nothing's going to touch rubber in terms of adhesion. Rubbers are always going to be your highest adhesion options. They'll get 15, 17 pounds at the same coat weight. In terms of LSE adhesion, so again, same peel tack, but off of a low surface energy type plastic. Again, solvent acrylic, UV acrylics are going to do about the same. You can put tackifiers in there. Emulsion acrylic, you can tackify emulsion acrylics, but again, because of all the other things I mentioned, all the other additives that are in there, you're never going to get as high as the other two. And again, because rubbers themselves are low surface energy materials, they're always going to outperform the acrylics there. In terms of shear, you get pretty good shear. Again, comparable shear out of the two, UV and solvent. Emulsion acrylic, you're going to get 1. Again, this is starting to improve, but you don't get really high shear out of emulsions because you don't get a lot of interaction between the polymer chains. Rubber, you get a lot of interaction there, so that's a 4. Now, in the temperature resistance, the UV and the solvent acrylics are going to be quite high. Emulsions, you're starting to get some temperature resistance there, and rubber PSAs are just terrible. Again, all rubber PSAs can be considered hot melts, even if you coat them out of solvent, which means they're going to turn molten as soon as the temperature starts going up. Once you get some interaction, high molecular weight of the acrylics and some cross-linking, they're really never going to melt again. So solvent resistance, the P there is for polar solvents. Acrylic UV, pretty high. With acrylics and solvents, you can get them to swell if you show them. So in if you're bringing in polar solvents, this is your MEKs, your acetones, your ethyl acetates, your alcohols. They won't redissolve, but they will swell in those environments. Depending on the amount of crosslink, it determines how much they swell, how much they don't, as well as some monomer selection. But emulsion acrylics, they'll do okay, but they will solvate. Rubbers actually do very good in terms of polar solvents. You can pour alcohol on a rubber, and because of the difference in polarity, it's not going to touch it. Now, when you get to non-polar solvents, again, same for the solvent acrylic, UV acrylic, emulsion acrylics, you can get a little bit more solvating there. And with the rubber adhesives, they're terrible. They're going to solvate right in. As soon as you put like a heptane, a hexane, or a toluene, rubber PSAs are just going to fall right apart. Plasticizer resistance, all the acrylics are going to get high marks there. Even the emulsions, again, really good at plasticizer resistance. See vinyls all day long. Rubber, terrible, just terrible with plasticizer resistance. They're going to fall right apart. Just chemical resistance, this is kind of all the above. This would be acids, bases, things like that, what didn't get covered before. UV, the solvent and UV acrylics pretty good. Emulsion acrylics, they do okay. There are some other chemicals out there that will attack them. Rubber PSA, depending what it is, we'll give it a plus. It could be a plus or a negative. So, but for this, and we'll rate it there. Water resistance, this is water resistance with detergent. So this is soapy water. And again, kind of like the solvents, polar, non-polar, acrylics can swell. The solvent and the UV acrylics, they won't dissolve, but they can swell. Emulsion acrylics actually do pretty good with water. It seems like an oxymoron, but it's the same concept of paint. It's pretty complex, but once they're dry, they actually don't necessarily want to redissolve. At least modern day emulsions are like that. And rubber PSAs, again, because of the polarity, pretty good, very good. UV resistance, you're going to get high UV resistance between the solvent and the UV acrylic. Emulsion, you get a little bit diminished UV resistance, and really this is more because of all the various additives that are in there. They are what's actually degrading and making it look bad. It's not the acrylic backbone itself. And rubber PSAs have very bad UV resistance. VOC and environmental, of course, solvent's not going to do too good there. UV acrylic, perfect. There's no VOCs to really worry about. Emulsion acrylics, again, it's water. You're not going to have any problems there. And rubber PSA, again, nothing there is going to be a VOC or environmental concerns. Outgassing and migratory is different. I'm going to go through these and show. So solvent, again, you have VOCs and then you have what's not reacted. What's not reacted could be residual monomer, and that's usually the case there, or any retained solvent, which could be under a VOC. UV acrylic, if it's not reacted in there, and if there's any monomer that isn't reacted, it's getting stripped off and recycled. Emulsion acrylics actually have a lot of outgassing. So all those other additives like the PVOH and there, the thickeners, the defoamers, and again, this is kind of the misconception. VOC really focuses on your organic solvents. So when I say VOC versus outgassing, if you put acetone on your desk or alcohol and then water, the alcohol is going to evaporate real fast. The water will eventually evaporate. If you put oil, vegetable oil, on your desktop, over a long enough period of time, it will actually evaporate, but it will take a long time. And so oil, therefore, is not considered a VOC, but it is outgassable. It will outgas. And my favorite example of this is Armor All. So you take some Armor All, you spray it on the dashboard of your car, you wipe it in, your dashboard's so nice and shiny, it looks great. 3-4 days, you start to notice a funk on the inside of your windshield. After 2 weeks, the shine of your dashboard's gone and you got this funky film on the inside of your windshield. Well, what happened was all of that material in that Armor All evaporated and condensed on your windshield. So again, it's not considered a VOC, but it is outgassing. And rubber PSAs, they have a little bit of this. The oil can outgas. Emulsion acrylics have a lot of outgassing. It's a lot of all those other additives that are in there. UV acrylics are the best for this, and solvent's going to have a lot of the unreacted monomer that's in there. So again, electronics, certain automotive specs, certain medical applications. If you need, if you need a really clean adhesive, nothing is going to outgas. UV is really the best bet. And this is why. So this is the difference between VOC and outgassing. When you look at the cost, solvent acrylic is going to be the worst. UV acrylics too, actually emulsion acrylic, you can run them more efficiently, or you can run them at a higher speed, and the polymer themselves are a lower cost versus the UV acrylic. I will say as you start getting up and trying to push the top end of the emulsion acrylics, get up about 2 mils, then actually the speeds do inverse and UV acrylic can be run faster. But because the cost of the polymer and how efficiently they do run, we'll rate them as a more cost-effective version than UV. UV is still worlds ahead of solvent, and here rubber actually kind of dominates that. Nothing's really cheaper than rubber. Looking at the thicknesses you can achieve up to about 5 mils of a solvent acrylic. It's about as high as you're going to get dried. UV acrylic, again, 15-20 mils is touted at the top end for some of the free radicals. Emulsion acrylic, you're only going to get 2, maybe 3 mils tops. And rubber PSAs, actually as much as you can pump, you can coat. We coat up to 50 mils on rubber PSA. Prevalence, that's how many of each adhesive exists. There are a lot of solvent acrylic options. So again, when you're looking for custom niche applications, UV acrylics can be formulated, they can be tuned, but there's not a lot of choices out there right now. Right now, that's in terms of the sheer number of adhesives that are out there for picking for custom niche applications, your solvent acrylic's going to win. There's a lot of emulsion acrylics out there, and there's a lot of rubber PSAs out there as well. So again, UV being new, it doesn't get a negative because there's a lot more options out there now, and that's increasing. But right now, in terms of the other technologies, there's just simply not as many available out there commercially. Tailorable, or how the tailorability of them. Again, this is how easily it can be done and the raw materials that are available. Solvent acrylics, very easy to tailor. You could buy something off the shelf and you can add something to it if you want to even tailor it, and it's very easy to mix, and there's a lot to choose from. UV acrylics, there's still a fair amount of raw materials to choose from, and there are more increasing every day. So I didn't give it a negative, but they are very hard to actually mix additives into. So they're not very easily done, but it can be done. Emulsion acrylics, between a 2 and a 3 here. It's very easy to mix something into an emulsion acrylic, but actually there's not a lot of options for what you can mix into an emulsion acrylic. in a lot of cases, actually, we find easier to find raw materials compatible with UVs more so than emulsions. And finally, for rubber, rubbers are very easily modified and tuned. In fact, in terms of all the adhesives, you can create just an infinite number of rubber-based PSAs. If you're talking solvent rubber, it's very easy to modify them. But if you're talking a hot melt rubber, it's difficult because of the same thing with UV acrylic. You got to melt it. You got to add the special mixers. So that gets between a 1+ and a 4+. So this is the summary here. Hopefully, I gave you an idea of some of the applications based off these attributes, and you learned something here. But I am pretty much finished, so we will open it up to questions. And Janet, I believe you're handling the questions.
Yes, that's right. So we do have a few questions that have been submitted, and I'll go ahead and just start off with why is there such a difference in the viscosity between solvent and hot melt adhesives?
So with hot melt, you can view hot melt adhesives as like lava. You're turning a solid into a molten. And lava doesn't flow very fast. The other thing with solvent-based adhesives, there's actually two things here, two answers. One, you can increase the viscosity of a solvent-based adhesive by simply not putting as much solvent in. And we'll assume, there are solvent blends you can do, but we'll assume the solvent blend is perfect. It works perfectly. You don't have to put as much in. The problem is, though, is that you never actually truly solvate the adhesive. You actually turn it more into a gel. And that doesn't coat very well, and you're not going to get good coating out of that. So you got to get it so that it's at least homogeneously mixed within the solvent. It's very equally dispersed. The other problem is that, as I described, the self-cross-linking adhesives, there's solvent in there, a high boiling point solvent that kind of keeps the catalyst from reacting. And as you start to increase the solids, and thus would increase the viscosity of a solvent-based adhesive, you really decrease the shelf life. So right now, solvent-based adhesives, self-cross-linking 3 months was a lot of the shelf life of ours. And then that eventually those cross-linking sites will find themselves even in the solvent, and they react. As you were to start to lower the solids, you're greatly going to diminish the point to the shelf life to the point where we probably wouldn't even be able to receive it and coat it. But we did look to, again, one of the ways you can run faster and run thicker with solvent-based adhesives is to increase the solids, which is reduce the amount of solvent. But you do hit an upper threshold because of those two things I just mentioned. So I think that pretty much answers that one.
Okay. All right. So the next question we have is that hang on one second. Okay, so do you think the government will ban the use of solvent adhesives?
Oh God, I love that question. So I did adhesives right out of college. I've been doing this about 20 years now. And the whole time I grew up in the industry, everything we always talked about was the government or the boogeyman's coming for you and your solvent adhesives, and they're going to step in. Now, who knows what government's going to do, because the pendulum always swings left to right, and the pendulum oscillations are getting much larger in magnitude. So who knows? But I would say most likely, I got maybe 20 years to go. I don't think the government's going to come in that amount of time and say you need to eliminate solvent. There's going to be two parts to this. If they did, let me say it like this: there's no need for them to do it. So one of the reasons why we always thought, early on in my career, they were coming is because we banned solvent paint. And that made more sense because solvent paint's being used by consumers, DIYers. It's being used in an uncontrolled environment. It's being people painting in their houses, and nobody knows how it's disposing of it. When we manufacture solvent-based adhesives or use solvent in a manufacturing industrial setting, it's very controlled. We have very tight regulatory regulations. We're audited, very tight regulations on how we can dispose of it. All the environmental controls, all the thermal oxidizers, solvent recovery, solvent entrapment, things like that. So it doesn't make sense for that to happen. So before I retire, do I think the government's going to come in and say no? Actually, I don't. With that said, by the time I retire, so we're talking about in the next 20 years, I actually think UV adhesives will overtake solvent-based adhesives, and that is really based off of 3 market principles. Inevitably, UV adhesives are going to overtake solvent. The advantages, there's too many advantages versus disadvantages, and they are just inevitably through evolution and the change. My opinion is that they will actually eliminate solvent-based adhesives, except for a few niche applications.
Okay, all right, great. Thank you, Steve. The next question is, don't the low molecular weight diacrylates used in UV pose some safety hazards too?
So UV adhesives do, I may not even say UV adhesives. In terms of inks and UV top coatings and early days of UVs, there was a lot of low molecular weight. So you could always tell what a UV was because you could smell it. Oh God, they smelled horrible, and they did cause a lot of issues. So again, UV is a lot like the electric motor in that UV technology has been around for a long, long time. It hasn't always been used in adhesives, though. It's been mostly in top coatings and inks. So the answer to that question is that for the adhesives, no. And the reason why is that the newest and latest, greatest generations of UV adhesives, everything is reacted into the backbone. So this is a reason why there's nothing that can outgas and there's nothing that's migratory, is that there's nothing free in there. Everything's reacted into the backbone of the polymer, so it can't go anywhere. So you don't have low molecular weight diacrylates anymore, or low molecular weight initiators or anything like that. Everything is reacted into the backbone of the polymer, so it's part of the polymer, therefore it can't go anywhere. And since it can't go anywhere, it's not really causing any kind of issues, environmental or health and safety type issues. And then the type of initiators we're using and things like that, they're just, again, we have all the DRAIS scores and everything. They're not very detrimental to the health. They pass ISO 10993, no problem.
Great. Okay, thank you. The next question is, are there any applications that use E-beam versus UV? That was the first part of the question, and the second part was, may we obtain copies of the PowerPoints? So I will answer a yes. Copies of the presentation and PowerPoints will be sent out to all attendees after the webinar concludes.
And this is also available on YouTube as well. With that said, E-beam, we haven't seen a lot of E-beam right now. Again, E-beam you see more on top coatings and maybe some inks. I see a lot of E-beams used in the packaging industry for top coatings. I'm not 100% sure why it hasn't really made its way to adhesives. Maybe because it's taken UV adhesives so long. But I know everybody that's really pursuing the chemistries for UV aren't really looking at E-beam. Now, if E-beam, you do run into some interesting, you do have to have an inert environment, which in web format. So probably the biggest thing against E-beam is that although you can inert a moving web, and even with UV, they say you got to have an inert environment. And I can tell you, nobody inerts anymore. That's kind of to the wayside. You don't need to have nitrogen or CO2 inertion in order to get a free radical UV cure going for an adhesive. With E-beam, it's absolutely critical because UV light will go right through atmosphere, but electrons will not. But a lot of your E-beam equipment out there is set up for food packaging and things like that. So you're talking stuff on the size of printing presses, 13 inches wide. It's a heck of a lot harder to make something like that and inert it 60 or 80 inches wide. So that's probably why a lot of the people out there aren't focusing on E-beam cured adhesives. But technically, E-beam can be used as well. It's just nobody's working on it at the very, very high level chemical industry level.
Okay, and it looks like this one may be a two-part question from the same participant. The first part of the question is how to improve the water resistance of a UV acrylic adhesive. So that's the first part, and I think this is a two-parter. And then it's which kind of adhesion promoter is good for this purpose?
So the UV adhesives are going to be up there with solvent acrylics in terms of water resistance. And again, they can swell. So one of the things is that, you know, acrylics can swell. So the way that you get acrylics not to swell, it's a two-part answer. One, you can increase the crosslink density. And two, it actually goes by monomer selection. So, and you know, being from a medical industry, you have sometimes MVTR, and the ability for a polymer to swell is a good thing. When you're talking skin adhesion, skin breathes, you always have perspiration, all this stuff coming out of the skin. You want a lot of moisture that go into the adhesive and evaporate off. That's called MVTR, moisture vapor transmission rate. That's good for medical. That's not always wanted though. The way we get good MVTR in medical is we use very hydrophilic monomers to make the most hydrophilic polymer possible. With an acrylic, although you'll never get as hydrophobic as a rubber, you can certainly pick more hydrophobic monomers, and you can go for a more hydrophobic type polymer. So you try to make, even though it's an acrylic, you try to make the most hydrophobic acrylic possible, and then you increase the you really increase the crosslink density. And in terms of the adhesion promoter, I'm not 100% sure what that means. I don't know if that means sticking it to a wet surface. In which case, a lot of times, just the rosin ester tackifiers that are commonly used, or something like, oh God, like the Crystal X, I forget what that's considered. I think it's styrenic. Some of the very hydrophobic tackifiers can be used. Ironically, even though rubbers are hydrophobic, they actually stick very well to wet surfaces, mainly because they're so hydrophobic, they push the water out of the way. So a lot of times by having hydrophobic additives in there and having a hydrophobic adhesive, that helps with the adhesion per se, helps make the initial bond. And again, I don't know what they mean by adhesion promoters, but it would help bond to a wet surface. And to resist the moisture, you know, it comes down to really picking the most hydrophobic polymer and increasing the crosslink density. And that goes for UV or solvent acrylic.
Okay, great, thank you. The next question is, are methyl acrylates better than acrylates for the water resistance of the bond?
Yes, I believe so. I'm trying to recall my polymer science. It's been a while since I dealt with this, but I do believe the methyl acrylates are better. I think they are less soluble. So you definitely use them, can use them in there. The problem is, again, they're very hard, so you can only use so much of them. So basically, you know, now we're talking 500 level chemistry class here. When you make an acrylic adhesive, you have soft acrylic polymer, hard acrylic polymer. Problem is with the methyl acrylates, whichever type you're using, they are better for your water resistance, but they do increase the hardness. So you're kind of getting out of that Dahlquist area where you get a little too firm and you're more on the elastic side than the viscose side. They can be used in there. You just got to watch your balance.
Okay, great, thank you. And it looks like the last question that we have is, does MacTac make all types of acrylic emulsions discussed? Solvent, UV emulsion, and rubber adhesives. And maybe what they mean is just acrylic adhesives discussed, not acrylic emulsions discussed.
Yeah, so with the emulsion and the acrylics, we coat them and we can formulate them, we modify them. We do not do the polymerization. With the UV, we don't necessarily do the polymerization, although we have designed a lot of those and have those toll manufactured for us.
And of course, rubber adhesives, we actually.
Oh, and rubbers, yeah, and rubbers, I'm sorry, rubbers we do formulate and compound them themselves. The thing with rubbers is that it's very easy. I don't want to say it's very easy. It's a lot easier to blend and mix adhesives than it is to physically polymerize. Polymerization is a massive step. So that's best for the large chemical companies of the world, the BASFs, the Dows, the Henkels of the world. You know, you see their commercials. They're the ones that are doing the paints and making all the ingredients for paints and architectural coatings. So a lot of it starts there. With the rubbers, though, you're not actually polymerizing anything. That's more of your Exxon Mobils of the world who are cracking the oil. They're doing that polymerization, and for it's blending. So those are a lot easier to work with. Again, with the UV, I'd say we have more of a hand in our UV adhesives, more hand in our fate, because we actually have worked with toll manufacturers and specified the exact polymer that we want. Plus, with UVs, it's a little easier in that you can make our own UV oligomers. They are basically polymers but smaller in size, and so you can actually do a lot of the chemical reaction on the web with just the exposure of UV light. That's not available in solvent adhesives. The solvent adhesives, all you really can do is evaporate the solvent. So whatever's reactive in there has to be in there beforehand. With UV, although you have to put it in there, it's kind of hard to put in the words, but we can actually have side reactions. And this is where we get a lot of our other properties in UV adhesives, and where a lot of the other properties come from is with the UV light that allows us to take a lot of these oligomers and build them into polymers. By exposing them to UV light, we get a lot of side reactions there, and we can modify them that way.
Great. I think that is it for the questions. So I would just like to thank everybody who joined us today. Steve, would you like to say anything in closing?
Yeah, hopefully you guys learned something. And I'm glad we didn't lose power.
Yeah, and there will be a follow-up email with a link to the live presentation that will include all of the PowerPoint slides as well.
Okay, everybody. Well, thank you for your time. This concludes our webinar.